Alright, hi everyone, welcome to this quick guide video on electrolysis. This is the first video and there's a few series after this. So make sure you have watched all the videos to get an overview of the entire chapter. Now to start off with this entire video, let's take a closer look at the setup of an electrolytic cell. Right, in an electrolytic cell, there's always the battery, followed by the electrodes, as well as the electrolytes. So these are the three key components. Now in terms of the electrodes, right, there's two different kinds. One is what we call the anode, one is what we call the cathode. Right, so for the anode is where oxidation happens, and for the cathode is where reduction happens. So a quick acronym will be anox with cat. Right, so that's how you remember which electrodes are you looking at. Now, regardless of the kind of questions that you come across, usually when it comes to electrolysis, there's really only two things to really consider about. First and foremost, what type of electrodes are we looking at? Are they inert or are they reactive? Now, inert electrodes means that they will not react, whereas reactive electrodes means that they have a possibility of reacting depending on whether they are the anode or the cathode. Second question we ask ourselves is, what is the type of electrolyte that we are using? Are we using molten substance or are we using aqueous substance? Because each of them will actually have different types of ions that's inside. Secondly, just an extension from this question, we also consider whether is it a diluted solution or is it a concentrated solution if it is aqueous to begin with. Because if it's concentrated, something might happen at the anode, right, that is unexpected when it's diluted. So let's take a look at a few examples and see whether we can apply these two questions to the scenario. First and foremost, let's talk about when you have inert electrodes. Now, inert means that they are unreactive. So there's only two unreactive electrodes that you'll come across. One is those that's made of platinum, the other one is those that's made of carbon, right? So in this case, the electrolyte is molten NaCl. So inside molten NaCl, there's only two types of ions. It's actually made out of only your liquid sodium ions as well as your liquid chloride ions, which are actually free moving. They can move around anywhere they want. But once you attach it to the battery, because of the charge that's given to this electrode, then now it's a negative charge over here, the sodium ion will start to move towards this electrode, and that's where the reaction happens over there. So we know that electrons flow out from the negative terminal in this manner, and the electrons will eventually enter this electrode and be used to react with the sodium ion. So you'll see something like this equation representing over here in yellow. Sodium ions will react with one electron to give you sodium. Now, why is it in a liquid state? Because we are looking at this question from the perspective of a molten NaCl. So it's most likely going to be very, very hot, right? If it's very, very hot, chances are that the sodium that's being formed is likely to be in the liquid state because it would have melted. At the anode, there's not much of a choice. There's only the chloride ions. These ions must be releasing out electrons so that this circuit can be a closed circuit. So the only way for chloride ions to go through a process that releases electrons is for them to go through oxidation, right? When they are oxidized, they actually loses electrons, and that's where the electrons come out. Now we always indicate as Cl2 because we know that halogens are diatomic. So there is unlikely to be a scenario whereby you come across chloride becoming chlorine as an atom, losing one electron. This is not likely to happen because chlorine exists as a diatomic molecule. So you always see a Cl2, and through that you can balance the entire equation. In this entire setup, you should notice that there's effervescence at the anode, and there should be a shiny silvery liquid, which is sodium, that's formed at the cathode. The overall equation can be represented as such. Let's take a look at another example, right? There's a total of 5 examples that we'll go through in this video. For this second example, we are still looking at inert electrodes, right? So it's still a platinum or carbon. Also to highlight that carbon can also be known as graphite electrodes, because graphite is a form of carbon. Okay, so now the electrolyte is actually dilute NaCl, right? So within dilute NaCl, there's actually a total of 4 different types of ions, because there's a sodium ion in aqueous state, there's also a chloride ions in aqueous state, which is quite standard. But because there is water inside, you also expect a small amount of H+ ions as well as a small amount of hydroxide ions. Now in this setup, it will mean that ions are going to move, and when ions move, they move based on the charge of the electrode. So you see your sodium and H+ coming towards the negative electrode, and you see your chloride and hydroxide going towards the positive electrode. At the cathode, which is over here, right, at the cathode over here, what happens is that between Na+ and H+, there is actually a choice of which one should go through the process. Now this is what we know as selective discharge. So between Na plus and H plus, as hydrogen is less reactive than sodium, H plus ions will actually be selectively, or what we know as preferentially discharged, or in this case it will be selectively or preferentially reduced to H2 gas, right? This is because of this difference in reactivity, and that's where we fall back into our understanding of the reactivity series. So in this case, H plus will go through the reduction, and the equation is represented over here, whereby 2H plus actually reacts with electrons to give you hydrogen gas. So you should notice that there will be effervescence happening at the cathode. Now in terms of what's happening at the anode, because you have a mixture of hydroxide or chloride ions, and since it's a diluted solution, you expect there to be much more of the hydroxide ions than the chloride ions. As a result, the hydroxide ions will be the one that goes through oxidation, and the equation is as represented over here, right? Whereby 4 hydroxide ions gives you 2 water, 1 oxygen, as well as 4 electrons. The oxygen gives you the effervescence. The overall equation over here can be represented as such, which shows you that actually what's happening here is that water molecules are going through electrolysis to form hydrogen gas as well as oxygen gas. We'll take a look at a third example now, and that is when you change the concentration, right? So now with the same condition as example 2 over here, just that instead of looking at a dilute solution, we're now looking at a concentrated solution. Now this change in term makes a whole lot of difference. At the cathode, Na plus and H plus wise, H plus will still be preferentially discharged because it is still much less reactive. Hydrogen is still much less reactive than compared to sodium. So what will happen at the cathode is rather standard. You still always go back to your reactivity series. But this time around, when you look at the anode, it's a bit different, because this time around, between these two ions, you realize that there's actually a lot more of the chloride ions, because you're looking at a concentrated solution. So when there's more chloride ions, it's more likely for the chloride ions now to be preferentially discharged. And as a result, what you see at the anode is actually that the chloride ions will form chlorine gas, and there will be effervescence again. So do take note that although these two equations, or rather these two setup looks pretty similar, the fact that you change the concentration does affect the reaction that's happening at the anode. In fact, throughout the entire chapter on electrolysis, you'll notice that usually it's the anode that requires a bit more thinking, right? Whether is it a choice of ions based on their concentration, or when the anode is actually reactive, now what will happen then? Okay, so anode is usually the one that we are more concerned about. There will be a bit of confusion, but for the cathode, it's quite clear cut. It's always based on the reactivity series. As you can see, the overall equation for both setups is also different. Now, in terms of example 4, okay, looking at a dilute solution now, and with copper 2 sulfate as the electrolyte. This time around, the ions that we're looking at over here is no longer sodium. We're looking at copper 2 plus. Likewise, the anion that we're looking at is no longer chloride. We are looking at SO42 minus. Now we are looking at the comparison between copper as well as hydrogen. It's important to take note that copper is actually less reactive than hydrogen. What this means is that because it's lower in the reactivity series, its ion, copper 2 plus, will be preferentially reduced at the cathode, and this will allow it to form copper metal, right? And we know that copper metal is actually reddish brown in color, which means that as this reaction proceeds, you'll start to see a lot of reddish brown solid forming along the edges of the electrode, because copper is being reduced. At the anode, one thing to take note is that ions that's as big or such as sulfate actually will never ever get discharged. Whether or not it's concentrated or not doesn't matter. It will never be discharged. So what we'll see in terms of observation in this entire reaction is that you'll notice effervescence happening at the anode because of the oxygen that's coming out. So you start to see a lot of bubbling, right, that's coming out over here. Now at the same time, on the right side, okay, which is on the cathode side, you'll see a layer of copper forming, right? So you see this electrode getting thicker and thicker, and this layer will look reddish brown in color. Now that is not all, because we are looking at the discharge of copper 2 plus ions into copper metal. What this means is that the solution actually loses copper 2 plus ions over time. And you expect the blue color to fade over time as it decolorizes because there's less of the copper ion that's inside. And that's for reaction example 4. Last but not least, we have example 5. Now if you take a look at example 5 over here, you realize that the electrolyte now is just water. And we know that water is actually a covalent structure. So, and covalent structures are not supposed to be a good conductor of electricity. So they're actually supposed to be poor conductor, except for the macromolecule graphite. Okay, so because water is a poor conductor of electricity, what we do is that we add in a few drops of sulfuric acid. Now what this do is that it provides some ions that's much needed to actually kickstart the entire conduction of electricity. So in this setup, what happens is that at the anode, you have your hydroxide ions, and the cathode, you have your hydrogen ions. These sulfate ions came from the sulfuric acid that you added in, but it's just a small amount, so we'll just ignore the sulfate ions, okay, so that it's not so confusing. At the anode, hydroxide ions will go through oxidation as usual, and the cathode, hydrogen ions will go through reduction. Right? These are pretty standard because there's not much of a choice. Right? And you notice that overall, you still see that it's actually the electrolysis of water breaking it apart into hydrogen gas as well as oxygen gas. Now with that, we have come to the end of this first video. Okay, I've went through a total of 3 different examples of what could happen if you are looking at inert electrodes. Now in the second video, we'll be taking a look at what if the electrodes are now reactive. Thank you.